I am Telmo Fontoura, an engineering physics student at Instituto Superior Técnico, and my project is Integrated Tactile Sensing for Robots, Wearable Devices and Human-Computer Interfaces. Since the dawn of time, humanity has been seeking to improve itself through knowledge search and through what one might call a rudimentary form of engineering. Nowadays, such enhancement is sought in modern science, engineering and technology. One technology paving the way into the future is nanotechnology. Accessing all the available knowledge gathered through the years and using the full resources of INESCMN, we propose to microfabricate a giant magnetoresistance-based sensor capable of mapping the magnetic field generated by the human heart, making this sensor suitable for magnetocardiography, which complements a simple electrocardiogram and produces, in many ways, more accurate results. Magnetoresistance is a physical effect in which the electrical resistance of a given material changes with the magnitude of an applied magnetic field. Giant magnetoresistance, discovered in 1988 by Albert Ferr and Peter Grunberg, is a quantum effect due to spin-dependent scattering of conduction electrons at the interface of a ferromagnetic and non-magnetic metal layers. It is observed in ultra-thin multi-layered structures composed of two ferromagnetic layers, separated by a non-magnetic layer, being the change in resistance related to how the magnetization of the two ferromagnetic layers align in relation to each other. A common multi-layered structure which presents this effect is the spin valve. One of the magnetic layers works as a sensing layer, free to rotate according with the applied magnetic field. So, by reading the resistance of the spin valve, it is possible to assess and map magnetic fields. We are faced with two major challenges to overcome. The heart's magnetic field is in the range of tens of picotesla, 6 orders of magnitude below the Earth's magnetic field, and presents a frequency of few hertz. So, we need to achieve this detectivity level at low frequencies with our sensors. For that, we will incorporate into our sensing device magnetic flux guides, which can increase the sensitivity up to 100 times. We will also minimize the dominant 1/f noise by implementing arrays of spin valves in order to reach the required signal-to-noise ratio. Ultimately, upon integration into robotics, specifically into a robotic hand's palm, our device will be able to make cardiac diagnosis without the need for a bulky and expensive setup, cryogenic cooling, or magnetically shielded rooms. This technology can be available to everyone in the coming years. The final objective is to develop a portable and quick cardiac diagnosis tool that could be useful at our home. If you want to know more, please follow my thesis work a few months from now.